Hello everyone. So in this video we are going to calculate the velocity of ultrasonic sound through different liquid media. So this experiment you can perform in the physical laboratory at your laboratory, and we can perform this experiment in virtual environment also. So I will demonstrate you how to do this experiment in virtual environment, and this will also help you in performing the experiment in the physical laboratory. So let us start doing this experiment. So what we are going to do in this experiment is I will elaborate how to perform this experiment, what is the logic and what is the procedure of performing this experiment. So you can see this screen here. What we have done is there is a scale provided. What we are going to have is, so this is the scale that is provided to us, and what we are going to do here is this screw gauge is going to put this reflector up and down whatever way we want to do it. Okay, and because this ultrasonic waves will be generated by this crystal here, so this is where the ultrasonic waves are going to generate, and this metal plates, you can see they are connected to this RF radio frequency generator. So that is going to generate the radio frequencies, and we are going to apply those frequencies to this crystal, and therefore ultrasonic waves will be generated through this crystal, and they will go in the upward direction, and when they get reflected from this reflector, they will travel back towards this crystal. In between these two going up and going down, they are going to produce the standing wave pattern. So that standing wave pattern can be either of this type. So the waves which are going from the crystal and falling on the reflector and coming back, they are going to produce this standing wave pattern. It can be either of this type, or it can be of this type, or it can be of this type. So what is our job is to put this screw gauge in such a way that the reflector reaches to the nodal point. So when the reflector reaches to this nodal point, you will get maximum current, and that maximum current we are going to note from this current meter. Okay, so what we need to do is put the reflector by adjusting the screw gauge at the nodal positions, and whenever we get this reflector at nodal position, you are going to get maximum current. So the effect that we are going to have, this is something like piezoelectric effect. So when we apply the mechanical pressure, you get maximum current. Okay, so our job is to get the standing wave pattern between the waves generated from the crystal and from the waves which are coming back from the reflector. And when they produce the standing wave pattern, if our reflector is such positioned with the help of that screw gauge that it is at the nodal position and the standing wave pattern is generated, you will get maximum of the current. So what we are going to do with that maximum of the current? So if we take this position of the reflector along x-axis and this critical current along the y-axis, so gradually the current is going to increase, and at certain maxima the current will start reducing. So what we actually see on the screen on the current meter is current starts from some minimum position, it reaches to a maxima, and if I further put that screw gauge to a higher position, the current reduces and goes to the minimum value. So if we are going to put this reflector somewhere here, then the current would be some minimum value, and as we put this reflector to a higher and the closer and closer to the nodal position, the current reaches to maximum once it is at the nodal position, and as we move ahead, the current drops to a minima, and again it starts increasing from certain value, and then it again goes to the nodal position where the current is maximum, and you can measure these two positions of maxima, and the difference between the two positions of maxima is going to give us this value of lambda by 2. So what we are going to with this value is this lambda by 2 will fetch us the value of lambda, and from that we know the equation velocity is equal to wavelength into frequency. So the frequency would be set at the initial setting of the experiment, and we know what the frequency is being set, whether it is 1 megahertz, 2 megahertz, or similarly something. And once that frequency value is known to us, and from these readings we would be knowing the value of lambda by 2, and we can get the value of lambda. These two values, when we put into this equation, velocity is equal to wavelength into frequency, we will get the value of velocity of ultrasonic waves into the given liquid media. So that is the logic of this experiment that we are going to use, whether it is in the physical setup or in the virtual environment. So here what we will do is we will try to understand what is the measuring setup. So this is the experimental setup that we are going to use. We can rotate this and we can remove it. We can feel the liquid here in this. This is the metal, the reflector, and once the cavity is filled with the liquid, we close it, and we are going to rotate this screw gauge, and this rotation of this screw gauge is going to move the reflector, and we can set it at different positions. So here we are going to note the main scale reading, and here we are going to note the circular scale reading. So the main scale reading we are going to note here where I am highlighting it. So 0, 1, 2, 3, 4, these horizontal lines 5, 10, these are the readings which we will take as the main scale reading. So this will give us the main scale reading, and here we are going to get the circular scale reading. So this is where we are going to get the circular scale reading. Okay, so this is where you will note the circular scale reading. So for this, what we need is the least count of the micrometer screw gauge. So how do we calculate this least count of micrometer screw gauge? Is formula we know, pitch of the screw and divided by total number of divisions on circular scale. So what is pitch of the screw? Pitch of the screw is defined as the distance moved by the spindle for one complete rotation. Okay, so what do we mean by that is, suppose I rotate the screw by a 360-degree rotation, the screw will either move down or up by certain distance. So that is the pitch of the screw. Okay, and pitch of the screw is equal to distance moved by the screw divided by total number of rotations. So suppose I rotate it for 10 rotations, and it goes from point X to point Y. So that difference between X to Y we can put it in numerator, divided by total number of rotations is, let us say, 10. So that will give us the value of pitch of the screw. So this concept how we are going to use in our this setup. So now you can see here the main scale is shown as a visible scale, and the circular scale is available with us. So what we can note is this total number of divisions on the circular scale is here. This is 45, 46, 47, 48, 49 and 50. So total number of divisions on the circular scale is 50, and if this distance from this 0 to where it is written as 10, if that is going to be 1 centimeter, so this distance is 1 centimeter. So what we can count is how many lines are there between this 1 centimeter. 1, 2, 3, 4, and there are 20 lines in this 1 centimeter. So what is the smallest reading that is possible on the main scale is this 1 centimeter divided by 20. So each line is having the value 0.05 centimeter. Okay, so 0.05 centimeter is the value of each line on this horizontal scale. So how we are going to read this? Here it will be 0.05 centimeter, it will be 0.1 centimeter, here it would be 0.15 centimeter, 0.2 centimeter. That is how it is going to proceed into this scale. Okay, so if we are going to have this least count, 0.05 centimeter divided by total number of lines on this circular scale, we have seen it is 50. So our least count will be 0.05 centimeter divided by 50 is 0.001 centimeter. So we need to note this, that our least count of this setup is 0.001 centimeter. So we need to get accustomed with this virtual environment. So this is what, when we go to the simulator, this is what we will see, or in the physical laboratory also this is the setup that we will have. So in physical setup it is not possible for us to have many liquids or set different frequencies, but in this virtual experiment it is possible for us to set different frequencies and perform the experiment for different liquid media. So from where we are going to choose the medium. So here there is a drop down given where you can measure, you can set the different liquid media. Okay, and where the frequencies would be given, so this is where the frequencies can be changed. So in this virtual experiment, the frequencies can be set from 1 megahertz to 5 megahertz. So if we slide, the different values would be there on this slider. Okay, with that, this is the on off button that we have. Then this is where you are going to get the current values. So we are going to use this gain button to set certain minimum current, and then we are going to use this adjust button to put it what maximum current you can have on the scale. So what is going to happen is from the gain, the starting point, when we move this screw gauge and put it at different positions, it will go till the adjusted current value, and then it will get deflect back to the minimum. So that is how the experiment is going to work. So this is where you are going to set the value of gain, and from this knob we are going to put the value of the adjusted current value. And these two black knobs we are going to use to move the screw gauge either to the lower values or to the higher values. At the initial positions it should be at 0, the main scale is 0 and the circular scale is also 0, and where we are going to note the readings is this inset where the readings would be available. Why this is set in the virtual environment like this is because we may not be able to see it clearly on the apparatus, so it is put in this inset so that we can see it more clearly and we can note the readings easily. So here what I will do is I will take you to the actual experiment where it can be performed. So of course what we can do is you can perform this experiment directly by searching in Google that you want to perform the experiment of virtual labs in the ultrasonic interferometer. So it can be done either way. So the keyword that I am searching is ultrasonic interferometer virtual lab, and this will give me the result that I want. Or otherwise what you can do is simply type vlab.co.in, and when we go to this vlab.co.in, it will open this website for us where all the virtual lab experiments are available. So if we scroll down, we need to go to this physical sciences, and in this physical sciences we need to go vlab.co.in, and we scroll down here. So what we need to search for is this harmonic motion and waves lab, and when we click here harmonic motion and this waves lab, we can scroll down and here is the experiment ultrasonic interferometer. So either way, by searching it in the Google by the keyword ultrasonic interferometer virtual lab, or otherwise directly going from this vlab.co.in, we can go to this experiment. So here what is available is this, with the different tabs are available: theory, how to perform the experiment, and then self-evaluation. So when we click on this simulator, this will open this simulator for us, and the image that I have shown is visible here. So what you can do is if this is not completely appearing on your screen, you can click here so that it goes into this mode where you can see the complete setup. So you can recall what I told you is this water, acetone, kerosene, castor oil and glycerin, these are the options available for different liquid media. So let us perform the experiment for water, and for different frequencies, either 1 megahertz, 2 megahertz, 3, 4 or 5 megahertz. So you can perform the experiment at different frequencies. So let us say we put it at 2 megahertz, and you can switch the power on from here or otherwise by clicking here. So now we have switched it on, and we need to put this gain at certain values. So let us say I put it at I can put it at 40, and then by clicking on this adjustment button I can put it at somewhere on 60. So these buttons are available to us, and what we need to take precaution is this gain is having a lower value as compared to this adjust. Why? Because this gain would be the starting point from where the current is increasing, and then it goes to the maxima till the adjusted point where we want the current to be maximum, and then there onwards it again comes back to the lower value. And now we can start taking readings. So what I have done is I have selected water, frequency is set at 2 megahertz, and I have adjusted gain at 40. I have adjusted this adjustment at 60 maximum current, and then I can rotate this screw gauge by this, and you can see now it has dropped to minimum, and I am scrolling by clicking on this black button, and there is nothing is changing here right now. So now you can see as we go to this nodal position, then it will go to the maximum current, and now it has started reducing. So where we need to note the reading is this point where it was having maximum. So what is the reading is, it is not showing anything other than 0. So your main scale reading would be 0, and where this line is coinciding is just before 40, so it is around 39. So your readings would be 0 is your MSR and VSR is 39. So that is what the reading you can note down. And then if we move ahead, it is going back and dropping to 40 minimum, and then I am still clicking on it, and it is going to increase now. So now you can see this is increasing, and it has gone to this maximum value. So one line has opened, so your main scale reading would be 1, and where it is exactly coinciding is the third line after 10. So your vernier scale reading or circular scale reading would be 13. So we will take one more reading, and then I will show how the observation table is to be used. So if I keep increasing it, so current has dropped, and now the current would start increasing gradually. So now it has reached to this maximum value. So I have gone one more point ahead. Okay. So this is where you need to take reading. So now what has happened is 2 lines are open. So your main scale reading would be 2, and it is exactly coinciding with the 36. So your vernier scale reading would be 36. So you need to note down this, and now I will show you from the presentation. So how I am going to manipulate the readings that I have recorded, how I am going to use it so that we can get the velocity of ultrasonic waves. So here you can see in this observation table I have made it for the readings of 1 megahertz. So these are the main scale reading that I noted. So when I perform the experiment, it would be 1, 2, 3, 4, 5, 6. So that is what I have written. Circular scale readings were 27, 27, 18. These were the circular scale readings. Now what I am going to do is these main scale readings is simply a number that I have noted down. So I need to multiply it with the smallest value of 1 each division. So we know, you can recall, it was 0.05 for one line. So I am going to multiply this each number by 0.05 so that I can get the actual MSR readings. Okay, so how I am going to get the actual MSR reading is number of lines multiplied by value of one line, that was 0.05. So 1 multiplied by 0.05 is 0.05 here. Then 2 multiplied by 0.05 is 0.10. 3 multiplied by 0.05 is 0.15. Similarly, you can put for all the readings. Now, how I am going to use this vernier scale reading is vernier scale reading multiplied by least count. So this was my circular scale reading or vernier scale reading, and I am going to multiply it by 0.001 centimeter. So that would be 27 multiplied by 0.001 is 0.027. Similarly here 0.027, 0.018, because I am multiplying 0.001 to this 18 value, so it is going to give me these values. So now our total reading formula is main scale reading plus vernier scale reading multiplied by least count. So what I am going to do is this reading here added with this reading here, that is going to give me the total reading. Okay, so this will be my total reading. So I am going to do it for all the readings. I am going to get these. Okay, so now what next I am going to do is, this was if you recall that graph that I have shown at the beginning of this video. So this is the maximum and this is the earlier maximum. So I am going to subtract this reading from this reading here, and I am going to get the lambda by 2 value, that is the D I am going to get. So each time I am going to do it from this reading, I am going to from 0.168, if I subtract 0.127, what I am going to get is this reading. So these are the consecutive, you need to repeat this experiment for at least 20 readings, and you will get these d values, that are the lambda by 2 values. So if I take average of all this, that will be my mean d value. So I have got this d value, and from this d I am going to get lambda by, this is actually the lambda by 2 value. So we need to recall this experiment was performed at 1 megahertz. So frequency was 1 megahertz, and this lambda by 2 is this value. So if we put everything, so how we are going to do calculations? Before that, I will show you this data set for the 2 megahertz. So these readings you can get actually by performing that experiment, by going to that link that I have shared with you, vlab.co.in, and you can search for that experiment, and this data would be available with you. And with that, now if we go to calculations, so for 1 megahertz and for 2 megahertz both we can do it. So the velocity v is equal to lambda into frequency. So d was average value we got, so this was lambda by 2. So this if I want to get the value of lambda, I need to multiply it by 2. So therefore it is 2d here, and frequency, so frequency is 1 megahertz, the d value is this, and 2 was from this formula. So the velocity that I calculated is for the water medium, it is 1360 meter per second, and for another setup for 2 megahertz it came out as 1782 meter per second. So actual value of this ultrasonic waves for the water medium is 1400 meter per second. So what is the error into this experiment, and what has caused these variations in the values, that you need to find out by going to the experiment. And if you get many values, if you perform the experiment for at least 20 set of readings, you would be closer and closer to what is the actual value of the ultrasonic waves into the different liquid media. So that is how this experiment of calculating the velocity of ultrasonic waves can be performed either in a physical setup or in the virtual lab experiment. Thank you all for your patience and watching this video completely.